Hi all, today we discuss Module 5 Information Storage Management. These are the contents discussed in this section: data consistency, the various type of local replication technologies, that is host-based replications. This will be again divided into two major important types: LVM-based mirroring and file system snapshot. Most file systems and databases buffer data in the host before it is written to a disk. A consistent replica ensures that data buffered in the host is properly captured on the disk when the replica is created. Ensuring consistency is the primary requirement for all the replica technologies. The file system buffer data in host memory to improve application response time. The buffered information is periodically returned to disk. In some cases, the replica may be created in between the set of intervals. Hence, the host memory buffers must be flushed to ensure data consistency on the replica. The given figure illustrates flushing of the buffer to its source, which is then replicated. If the host memory buffers are not flushed, data on the replica will not contain the information that was buffered in the host. We can achieve replication for the file system in two ways. First one is unmounted, second one is mounted. If the file system is unmounted before the creation of the replica, the buffers would be automatically flushed and data would be consistent on the replica. Otherwise, we would require other kind of activity on the replicate file system. C is a primary requirement to ensure the usability of a replica device. Replication can be performed with the database offline or online. If the database is offline, it is not available for input-output operation because there is no updates are occurring. The replica will be consistent. Suppose if the database is online, it is available for input-output operations. So many transactions are updating the data continuously. So when a database is backed up while it is online, changes made to the database at this time must be applied to the backup copy to make it consistent. Table shows that how consistency is achieved in both file systems and database through offline and online methods. In this session, we discuss how file system consistency is achieved through flushing host buffer. In order to achieve consistency of a file system, the file system buffer data in host memory to improve application response time. This buffered information is periodically returned to disk. In the case of Unix operating system, the synchronization is a process that will flushes the buffers to a disk at a set of intervals in order to achieve the consistency. So that the host memory buffers must be flushed to ensure data consistency on the replica prior to its creation. If the database is online, it is available for input-output transaction. So that so many transactions to the database update the data continuously. When a database is replicated in its online, changes made to a database at this time must be applied to the replica to make it consistent. So that dependent right principle is used for this purpose. It is used in many applications and database management systems to ensure consistency. According to this principle, a write input output is not issued by an application until a prior related write input output has completed. For example, a data write is dependent on the successful completion of the prior log write. Dependent write consistency is required for protection against power loss, loss of local channel connectivity, or storage devices. When the failure occurs, a dependent write consistent image is created. A restart transforms the dependent write consistent image to a transactional consistent image. The given figure shows that how dependent write principle works. For example, A data rate is dependent upon the successful completion prior to the log rate. If a transaction is said to be completed, database requires a series of writes to have occurred in a particular order. These writes will be recorded on the various files and devices. When the replica is created, all the writes to the sources devices must be captured on the replica devices to ensure the data consistency. The figure illustrates the process of flushing the buffer from host to source. Input for outputs 1 to 4 must complete in order for the transaction to be considered completed. Input output 4 is dependent upon input output 3 and will occur only when input output 3 is complete. Input output 3 is dependent on input output 2, which is in turn depends upon input output 1. Each input output completes only after the completion of the previous inputs. Figure illustrates the process of replication from source to replica. Input-output transactions 1 to 4 must be carried out in order for the data to be consistent on the replica. Creating a point-in-time copy of multiple devices happens quickly, but not instantaneously. So it is possible that input-output transactions 3 and 4 were copied to the replica devices, but input-output transactions 1 and 2 were not copied. So in this case, the data on the replica is inconsistent with the data on the source. If a restart were to be performed on the replica devices, input-output for which is available on the replica might indicate that a particular transaction is completed. But in all, the data associated with the transaction will be unavailable on the replica, making the replica inconsistent. Another way to ensure consistency is to make sure that right input output to all devices is held for the duration for creating the replica. This creates a consistent image on the replica. Databases and application can time out if the input output is held for too long. Various type of local replication technologies are host-based replication, network-based replication, and storage-based replication. File system replication and LVM-based replications are examples of host-based local replication technology. In the case of LVM-based replication, the logical volume manager is responsible for creating and controlling the host-level logical volume. An LVM has three components: physical volumes, volume groups, and logical volumes. A volume group is created by grouping together one or more physical volumes. Logical volumes are created within a given volume group. A volume group can have multiple logical volumes. In LVM-based replication, each logical partition in a logical volume is mapped to two physical partitions on two different physical volumes, as shown in the figure. An application write to a logical partition is written to the two physical partitions by the LVM device driver. This is also known as LVM mirroring. Mirrors can be split and the data contained there can be independently accessed. LVM mirrors can be added or removed dynamically. Advantages of LVM-based replication technologies are: it is not dependent upon vendor-specific system. At the same time, it is a part of the operating system and it will not require any additional license is required to deploy LVM mirroring. In this session, we discuss the limitations of LVM-based replication. As every write created by an application translates into two writes on the disk, an additional burden is placed on the host CPU. This will be reduce the application performance. Presenting an LVM-based local replica to a second host is usually not possible because the replica will be part of the volume group, which is usually accessed by one host at any given time. Tracking changes to the mirrors and performing incremental synchronization operation is a Challenge for all VMs do not support incremental resynchronization. If the devices are already protected by some level of read on the array, then the additional protection provided by mirroring is unnecessary. This solution does not scale to provide databases and applications. File system snapshot is a pointer-based replica. It requires only a small amount of space compared to the original file system. This snapshot can be implemented by either file system itself or LVM. It uses copy on first write principle so that when the snapshot is created, a bitmap and block map are created in the metadata of the snapshot file system. This bitmap is used to keep track of blocks that are changed on the production file system after the creation of the snap. The block map is used to indicate the exact address from which data is to be read when the data is accessed from the file system snapshot. Immediately after creation of the snapshot, all reads from the snapshot will actually be served by reading the production file system. In the case of a copy on write principle activity, if a write input output is issued to the production file system for the first time after the creation of a snapshot, the input output is held. The original data of production file system corresponding to that location is moved to the snapshot file system. Then the write is allowed to production file system. The bitmap and block map are updated accordingly. Subsequent writes to the same location will not be initiated by the copy on write principle activity. In order to read the data from the snapshot file system, the bitmap is consulted. If the bit is 0, then the read is directed to the production file system. If the bit is 1, then the block address is obtained from the block map and the data is read from the address on the snapshot file system. So that snapshot file system requires small amount of space compared to the production file system. In these sections, we discussed how to obtain consistency in file systems and databases. Second topic, host-based local replication. Thank you.